We did carry lookahead adder, ripple carry adder.
Addition process was complete in that DST1. Okay, like fast adders we didn't take up. Okay, we have a segment of like fast adders, Booth's concept, Coxstone adder, Root-Kung adder, different types of adders are there. Okay, that along with one topic which is left over in the last chapter we will complete today. So you remember that rules of one's complement, two's complement, or sign magnitude addition, I suppose. Remember them? The topics, okay. And I think the last topic what we have, where we have stopped, is the built-in self-test, I suppose. Yes. BIST we have seen. In that BIST, I think linear feedback shift register, that is the other name of pseudo-random pattern generator, was explained. And what were the different tabs we have seen? What is the meaning of these tabs and all? Tabs. Unable to recollect. Unable to recollect what is tab?
Is it the test axis port controller?
Can you repeat?
The test axis port controller?
Okay. That is the other one. Okay. The actual tapping in your linear feedback is where the feedback to be taken. Okay. Tap controller is different. Tap points is different. Okay. Tap controller is the one what you are saying. Normal tap is when you are taking 4-bit shift register or 5-bit shift register. That way we have taken something like until 32-bit shift registers. Now, in linear feedback shift register, if you have different number of registers, where exactly we need to take the feedback, or like something like we have taken example for 4, wherein your Q1 and Q4 sort of thing, they were taken as an XOR, and this feedback is taken to this D1. No? This point where we are trying to take the feedback, that we call it as taps. Okay, the tapping point. Tap controller is test axis port controller. Okay. So what is the type of feedback we are giving in? What is the type of feedback that we are giving in? If you remember your circuit, hope you should remember, because this is your mid portion. Say 4 flip-flops are there. Sorry, Q1, Q2, Q3, and Q4 are the outputs. We were taking this as an XOR, and we were feeding back that to D1, and this goes to D2. Q2 goes to D3. Q3 goes to D4. And this is with respect to simple or what you say synchronous clock. Just for recollecting, I am doing this once again. Okay. So my question is, what is the type of feedback what you are taking in? This is an XOR operation, means that it is modulus or what you say mod 2 addition. That means in a linear operation we are trying to perform. So that's the reason linear. We are taking a feedback, and this is a shift register. So LFSR we were saying that is the a name derived for based on its function. The other way is that the patterns that are generated are pseudo in nature. So pseudo random pattern generator. Okay. What is the exact use or what is the need of this linear feedback shift registers in your testing? This is in regard with the testing we are asking. I think to generate the test patterns. What are these test patterns? Are they something different from the combination of the binary bits? We are saying test patterns. What are they? They are the binary combinations, no? Binary combinations, and we need to compress them. Compressing the test pattern, or what you say, the compression of the total test outputs. Generating the test pattern and compressing them into what we call it as signatures. We were using this, what you say, the shift register format setup. And normal shift register, if you take normal shift register, I'm putting the question in this form. Normal shift register, if you are having, what is the function it will be allowed? Hello? Hello? Good morning, class lo unda cheppandi. Cheppandi. Just పంపించే Some disturbance. Okay. So generating these test patterns and compressing that into signatures. I think the meaning of signature, we have seen that in the last sessions. It is the combination of the bits. Okay. A compressed form of the combination of the bits for which the circuit is to be tested for. That is called as the signature. Now, say if you have n-bit shift register, normally a shift register, if you consider, it is the operation something like shifting the data from one side to the other side, something like directional change of right shift or left shift you'll be taking, na? Or something like we can do the operations with serial parallel. These were the operations what we have seen as for the shift register is concerned. But now we taking this feedback element, we are able to generate. That means this shift register circuitry is little bit less complex. Something like if you use a counter, you need to have some what you say, a clock segment, a conditional output coming over. All this little bit of one-step complexity will be more to generate a sequence, or what you say, the combination of bits. So for that, maybe shift register with a simple feedback element, if you take. Someone was speaking. Mute your mics, okay? So here, if this shift register is used with an modulo 2 addition operation, taking different tap points for depending upon how many number of flip-flops you are using, we were able to generate 2 power n minus 1 combination of test patterns. Okay. And if I give one signature, my just put a hearing ear now. If I give one signature out of the possible test patterns, what is the probability that there will be a matching of the pattern? Is there any answer? One input sequence, one combination of sequence you are putting in, and you are trying to do a comparison or something like mapping sort of thing. How many or what is the probability with how many sequences that one single combination will be able to be matched? How many? I think no one is hearing, just logged in. There is no answer. How many of you are there live here?
1 by 2 power n minus 1.
1 by
2 power n minus 1.
power n minus 1. Okay. If this is the all possible combination of the patterns that are possible, if you give one sequence for testing, the what you say correct signature mapping will be 1 of 2 power n minus 1. Okay. What is this n minus 1 sort of thing? All zeros were not possible with this setup. All zeros were not possible with this setup because something like we were taking the pattern with use of the preset element, and we were presetting one of the flip-flop, and we were trying to generate 2 power n minus 1 combinations. Okay, that was the thing. If you remember the what you say, the pattern of generating the signatures earlier is using a preset. We were presetting one of the output of the flip-flop, and we were trying to push that pattern along with this feedback parameter, so that we were able to get that 2 power n minus 1 whatever we were saying. Then what about that all zero pattern is that, say if I take the q bar element, q2 bar, q3 bar element, okay, and that means n minus 1 negated outputs if I take, and that I try to take it back into the XOR input, I'm making this system to be ready for generating all zeros. Like when this all zeros thing may happen is that if Q1, Q2, Q3 and Q4 are 0, 0, 0, 1. Okay. After this, what happens is we are taking the negation of Q1 bar, Q2 bar and Q3 bar. That means negation of Q1, Q2, Q3 we are taking. And what is your feedback? This is Q1 XOR with Q4 already available. And we XOR one more extra parameter of Q1 bar, Q2 bar and Q3 bar such that say if this is 0, 0, 0, 1, actually this will be giving you 0 XOR with 1, that is D1 will be 1. Okay. And Q1 bar, Q2 bar, Q3 bar will be 1. That 1 over this 1, that means 0, 1, 1 XOR, you will be getting 0. This 0, if you update, you will be getting all zeros. This 0 will be shifted, no? This will be shifted and this will be 0, 0, 0, 0. So that was the, what you say, an adjustment that is made in order to have all zero pattern also. So until this was your class test it, test the pattern, or what you say, pattern in the sense test the circuit with the pattern. This facility, if it is there, normally what is the element of this BIST is that it should be having some self-test which is built on the IC itself, which is built on the circuit itself. That is the main focus of this BIST architectures. So when I can have this to be 1, I'm getting 1, I say it is properly Okay, there was a power problem. Yeah, this test pattern has to be mapped with your circuit which is under test, and something like a comparison element. If you consider, if both the outputs are similar, then we say that that circuit is working properly. Similarity means all the inputs you give the same fault-free output if you are getting, then we can say that they are working properly. Okay, this is general logic that. Now, here, if you remember in your RAM testing or ROM testing, something what we said is a controller is available.
Ma'am,
Yeah.
ma'am, could you please go back a few minutes back, ma'am? Because of current fluctuations, we couldn't hear properly.
Even I had a power problem. Okay. Oh, this was the only point. Okay.
Yeah, okay, ma'am.
So this BIST controller, what I was telling is, what is the purpose of BIST and how we are able to use this for testing the circuit. That was the concept. Okay. This element of LFSR, if you have taken, this is generating element, and we need to have some testing setup also. That means we need to compare these two patterns we were saying. If you are getting a, what you say, zero comparison in the sense a simple XOR operation sort of thing or a comparison sort of thing will be taken, wherein your fault-free response and your system response, or what the circuit you are testing, that response both are matching or identical. We can say that the circuit is properly working. For that, what is the element or what is the setup we have on our circuit is a BIST controller which is controlling what to be generated or what to be released or what to be analyzed sort of thing. This is a controller element wherein we have something like read write data, your address format sort of thing, right address, and what you say, this address counter we had, and onto which the circuit under test if you are taking, say if it is a RAM, you are taking this write data and the address bit. From that, something like this is data, input data you will be taking. Okay, and this is the address location. From there, you will be reading out what is the data that is available here. So maybe output data if you take, until this was something like generating sort of thing. So this is what we have is, this is the response of the system, response of the circuit after applying the test pattern. Now how to compare this, or what you say, how to say that this circuit is working properly, how to say that, or how to validate that the circuit is error free, is that the response that your design is giving for a specific input. That means your test what you are applying. If you can take that and what you say, somewhere you store the what you say, fault free response, fault free response and this response, if you can compare, something like you compare these two, this will be giving you whether this is, circuit is properly working or not. Okay. Now we try to compress this segment of what you say, the fault-free response, the response of the circuit, and comparing that. This, if I can compress that, and I can have both applying the fault-free response and taking the response of the circuit under design and comparing all these functions, if I can put that at one slot in one shot, that we call it as multiple in signature register. Okay, this multiple in signature register is nothing but like it has the provision of what you say, applying the fault free response and taking the circuit response and comparing them. The setup of what you say, generation and testing both will be there. Okay, what extra element or what you say, what is the circuit changes that are needed in order to make a linear feedback shift register to a multiple signature register? This is generating element. Okay, like comparison, if we want, we need to have an extra setup. Is that we use XOR operations because comparisons will be done by XOR element. The logic of XOR will be giving us whether the bits or the patterns what you are getting is similar or different. Okay, so an XOR extra element of XOR is taken at every stage or every bit, every tap point. Then that will be making linear feedback shift register into a multiple in signature. That means not only generating, also testing can be done parallelly. So what is the difference we have from the previous circuit is that if you take this setup of 4 shift registers with a feedback taken from the first and last path or something like first flip-flop and the last flip-flop, this is a normal LFSR. Now what we do is for each stage or in between each flip-flop, we try to take one more set of XOR operator in such a way that each XOR operation will be provided with the system response and the external test pattern or the pattern that with which we want to compare. Okay, so something like this. Now this is your feedback path. As usual, this is D1 and this is Q1. Now this Q1 along with external input and this feedback along with an external input, if you take this, this setup makes it as a multiple in signature register. That means what are the things what we are taking is this we feed with an external Z1, Z2, Z3 and Z4. What is the meaning of Z for our digital circuits? X, Z, Y's. What is the meaning of this for us now? These are inputs, these are outputs, and these are the states. No, this is the standard representation. X, set of X means inputs. We represent that with X. Z means set of the outputs will represent that with Z. And Y is the status. Now what we are taking here is only the outputs. That means the system response. The response of the circuit that will be given out. So the output of the circuit will be fed to the linear feedback shift register in such a way that this parallelly the test pattern here what you are getting from this shift register will be compared with the system response. This is your system response that will be compared with your test pattern. Now if they are same, then your output of this will be 0, else it will be different. That means you will be getting as 1. Means that out of 2 power n minus 1 combination, only one will be getting the all 0. The others will be, if any change or any bit value change is there, you'll be getting the corresponding bit to be 1 instead of 0. Okay, so okay, so this multiple in signature registry, if that setup is available on your system, you are giving a space for the circuit to test itself. Okay, test itself its own response with the test patterns what you are giving. So here for this built-in self-test, there are several architectures available, and in these we have 2 what you say main type of architectures for built-in self-test. there are two main architectures. What are they? One is stumps. Second one is Bilbo. What is this stump is? This is self-testing using M stands for multiple in signature register, okay, and P stands for parallel and parallel. S stands for SRGM. SR, this S stands for SR. You can say SG also, because this is shift register. S stands for shift, R stands for register, shift register, sequence generator. So this is your stumps, STUMPS, okay. And the other one is built-in logic block observer. Built-in logic block observer. This is Bilbo, okay, BILBO. So these are two architectures what we are having. The first architecture we can say this as test per scan architecture, and this we call it as test per clock. What is this? We'll see. This is test per scan. Your stumps is called as test per scan architecture, and Bilbo is called as test per clock architecture. Or something like here, if you take this stumps architecture, or the stumps will be having a setup of what you say the scan chain. The scan chain earlier classes we have seen something like the set of total shift registers which are acting as in-out setup. Okay, boundary scan cell. Hope you remember that. So this stumps will be having again this BIST is the controller. The BIST controller will be used, and this through the BIST controller, something like a pattern generation should be available for us. A pattern generator, and the scan chain will be used. So scan chain is, this is the same scan chain what we have seen in the boundary scan. Sorry. The same scan chain we are using here. So how many number of elements you are using, how many number of bits are there, the size of the scan chain depends now. So if you remember that scan chain will be having something like scan in, scan out sort of thing, scan data in, scan data out. Okay, that scan chain will be like what you say, the through that scan chain, the pattern of the bits will be shuffling or what you say shifting. Okay, so this will be controlled by the BIST controller, wherein the pattern generator, normally we can take it as the test pattern generator, will be giving its test. Okay, and the BIST controller will be giving the bits of the scanned element. Now, after the normal iteration performed on the circuit, the response of the circuit will be taken onto the scan chain. If you remember, circuit on the test, if you are taking towards your left side and towards your right side, you have the what you say the registers. No, if you remember, towards the left side, if you take this becomes the input side. That means the one which is giving the data to the circuit, and towards your right side will be the one which is taking the response of the circuit. If you remember, one set of the registers. Same if you take for the second circuit, this set of registers becomes the input provider, and the next set of flip-flops becomes the output catcher. Okay, this is the way we were seeing. No? This is through your scan chain. We were taking out the response of the total design or total circuit. Scan data in, scan data out, if you remember. Okay, so this setup of this scan chain is used here, wherein what to be what you say given as the input for generating the response of the design will be provided by both this test pattern generator and the controller shifting the data. Now, after one time lapse or one propagation delay means for us is that the total time needed for the total setup of the scan chain to generate a new value. Okay, so this gives the response, and this response has to be taken and analyzed. So what is that we are analyzing is the test response analyzer. Test response is getting analyzed. Okay, now here what is the way we are trying to perform is now scanning first the patterns from the test pattern generator. Scanning first the test patterns. Normally here we can use linear feedback shift register setup, generate the signature. You try to put or dump these test patterns onto the scan chain. Okay, that means onto all the scan chains you will be dumping the pattern. Now, using the BIST controller, switch over to a normal operation. What will be a normal operation? A shift register operation. While you put it into a normal operation, okay, what happens? With respect to the system clock, you will be getting the output for what you say 1 clock. You'll be getting the output generated for a 1 clock for each bit or what you say each scan element. And now after getting the response, you shift that the response of the output here, shift the output or what you say the response from the scan chain. You gather the response and you try to analyze that what is the response this circuit is giving you. Is it as per the fault free circuit response or any deviation is there? So here we can use multiple in signature register or what you say you can use here a MISR setup where you have the fault-free response and the response of the system both compared and giving an analysis whether your circuit is working properly or not. Okay, now what is the complexity of this design is, say you have 100 or 1000 something like scan chains. Say. In a total what you say the setup in this scan chain means what you say it is the setup of the registers. That means this becomes one chain, this becomes one chain, this becomes one chain. So total number of scan cells, boundary scan cell, I'm speaking of this as boundary scan cell. A combination of boundary scan cell is the scan chain. Say total design you have 1000 scan cells. Okay, it needs how many clocks to generate the test pattern is 1000 clocks. How many boundary scan chains you have or how many boundary scan cells you have, that many clocks are needed. That means first all these scan cells has to be filled with the patterns, that are generated from the LFSR segment. Okay, and you give one test, okay, you give one test, or what you say, one iteration time, one test time or one iteration time to scan or to generate the response of the overall design. Okay, so that's why we call this as test per scan. Stumps is called as test per scan. Okay, say if you need to reduce this time, here this is dumping, here this is collecting, or what you say, this is inputting the test pattern and this is collecting the test pattern. Now, waiting for the pattern to generate and again afresh you load the new pattern, maybe once this test pattern is dumped onto the chain, this fellow is vacant. You can utilize this duration for inputting a new test pattern, or what you say, inputting the new test pattern or generating the new test pattern. You can use that too. And parallelly, this operation can be performed. Okay, filling the chain and scanning out, or what you say, the parallelly loading of or this analyzer can be done. Inputting and parallelly testing the response can be done. That cut shorts some time of what you say, the testing. Okay, so this is something what we you can visualize this as the number of clock pulses which is required will be equal to the number of flip-flops. Okay, the number of clock pulses here needed will be equal to the longest chain. That means here we are saying chain in a loose form, but this chain can have different number of boundary scan cells. Different number of boundary scan cells. That means here you can have 5, here you can have 10, 15. It depends. Like based on how much space you have, you are accommodating that number of flip-flops there, or what you say, the scan boundary scan cells. Now, the number of clocks which are needed, or what you say required, will be equal to the longest scan chain. Okay, longest means something like this. See, here I have 5, here I have 10, here I have 20. Say. This is the longest chain, we can say. So, at least 20 clocks are needed, or 20 cycles are needed to complete, okay, to complete what operations? To complete the scan in, one capture, and to scan out. To scan in, this one is scan in, this is capturing, and this is scan out. So altogether, how many you need? Say, if the longest number, say if I name this as say P is the longest. How many we need is 2P plus 1. Why 2P? One set of P clocks for dumping, one set of P clocks for gathering, one is for capturing through the scan chain. So 2P plus 1. This is very lengthy. Obviously, we are saying though your circuit is very simple, this is very lengthy and it needs many more, what you say, clock pulses to perform the iteration of testing and generating the test pattern and analyzing. So the alternate for this is, though the circuit becomes little bit more complex than your stump architecture, it is not a test per scan, but it becomes a test per clock. One complete test can be completed within one clock. But here we need to wait for all the chains to be responding. That's why we are taking these many number of clock pulses. More number of clocks are needed. So that means this is circuitry wise, this is simple. Stumps is simple. But the time taken for what you say dumping and testing both needs many clock pulses. So testing is very slow. Instead, if I can accommodate some portion of the shift registry for testing and the some portion of that shift registers for what you say loading, generating and testing, or what you say loading and testing. Both the things, if I can divide that, and a moment I use the first setup as a generating element, the second setup as the testing element, I can shift this. Say I have a circuit here, this generates the test pattern, collects the test pattern. Okay. When I use another circuitry for testing, say this is C1 and this is C2, I can use this setup for generation and this setup for testing. That means I can have the flexibility of interchanging the what you say the portion, interchanging the functionality of that setup of the registers. That is nothing but the built-in logic block observer format, which is a test per clock format. Okay, so here we can use what is the flexibility you have in this built-in logic block observator is that the element of registers, the registers in your Bilbo can be used in such a way that some setup you can use that for generating the test patterns. Some setup you can use for testing. So multiple. If you are not testing, it should be a normal operation. Either you can use into normal operation. A normal operation means something normally shifting the data. Okay, so based on what is the type or what is the role at that moment your circuitry is posed for, it will be performing that operation. Okay, so you are using this into something like shuffling between some modes. Either you can use that as a generator, testing, normal, or normal shift register. Normal shift register. You can switch this into any of these mode based on the what you say control signals. Now this registry setup in the built-in logic block observator is not scan per what you say test per scan, but it will be a test per clock. Test per clock. Okay. Something like where you can have different circuits set up. As I said, you can have different circuits set up using the setup of the Bilbo in between the circuits what you are testing. Say, if this, I take this as the built-in logic block observator block, which I am placing in between the circuit what I am testing in. Okay, say if this is my built-in logic block observator Bilbo. Okay. Now I take this as the circuit under test. Say first circuit and this is second circuit. What we are saying is this setup of the block observator is that you have the operation of LFSR multiple in signature or normal shift register available in this setup itself. Only thing is that portion whether you are using that for generation or testing will be decided by the control signal that is available on the architecture now. Okay, so if this is your input portion and this is your path of output, but when you are testing the circuit one, okay, this setup becomes the linear feedback shift register or pseudo random pattern generator when you are testing circuit 1. And this fellow, the second setup of the Bilbo, this will be gathering the system response, and this will be testing using an XOR operator. So multiple in signature register. This is for circuit 1. If you are testing, or if you are testing this circuit 2, what happens is this. Now this becomes the, what you say, this is your first and this is your second, say. This is the path to take. This becomes linear feedback shift register, and this becomes multiple in signature register. Okay, this is just for idea I'm giving in. Now, if I totally put this, see here, what we need is one pair of Bilbo setup for one circuit. One pair of Bilbo setup for one circuit. Is that correct? One pair of Bilbo setup for one circuit. Okay. Now what I do? I remove this. Just for understanding, I gave the earlier connectivity. Now what I do? When I am testing the second circuit, what I do is, when I am testing the second circuit, I use this setup, this as linear feedback shift register. Okay, and this element I'll take it back here. Sorry. This I'll take it as multiple in signature register. Finished. For testing circuit 1, this Bilbo 1 and 2, 1 becomes generator, LFSR, 2 becomes MISR, multiple in signature. For circuit 2, 2 becomes LFSR and 1 becomes multiple in signature register. So we are able to slice this Bilbo into two functions. Parallelly, you are able to perform the iteration of generation and testing. That is as simple as that. Okay. Now for this, what is this Bilbo setup? What is this Bilbo setup? It is again the same shift registers. One second. So here, shall we have a break or continue? We'll continue. Shall we have a break or continue?
Break.
No one is there. Everyone is on break right from 10 o'clock. Only I am speaking something here. Blah blah blah. How many of you are sincerely listening? Tell me. At least one student is there. Today I am not going to share the video. Damn sure. Because there is no response. Everyone logged in and left. Varun and Dheeraj, are you there?
Yes, ma'am.
Who is that? Varun or Dheeraj?
Varun, ma'am.
Not even a single student is responding. Huh? Everyone has reached the campus.
Yes, ma'am. All of us all.
Almost all. Okay, what happened to this classroom thing? Got adjusted?
No,
I'm
ma'am.
I'm
Actually,
giving a break for 10 minutes now. I'm speaking with CR. People can take break.
there is only
Your,
one class, I think, ma'am.
uh,
That class
Varun,
is working. Yes, ma'am.
Varun, your voice is breaking. Yeah, Varun, what about the other subjects?
We have to discuss with other faculties, ma'am. Like, there'll be
They are
one
taking
subject.
offline or online? Are they taking
One
offline
subject
or
is
online?
one subject is confirmed offline, ma'am. Other subjects we have to.
Offline. Offline, how they are conducting? Was it any one class held?
No, ma'am, not yet. So,
Whose subject is that? Offline?
Ravi Kumar, sir.
Okay, so two sections he'll be handling in the same slot or two different
No, ma'am.
slots?
Two different slots. Sir said that he had to take offline for complete class, not hybrid. So, sir was like, I'll take both sections at different timings.
Okay. But I think what I'm seeing is taking online, people are not responding. You people are just logging in and no one is responding. That is waste also. Maybe taking offline will be looking better if you people are not responding. Because when you are at your places, at least 30% response was there. Now I'm not seeing only one student was giving me answer. Hmm? Sort it out, like whether you have the timetable divided for section A and section B and different slots are given, you find it out. Because online, once you come back to the campus, taking online means it is not giving any meaning because you people are not responding to the classes. Like just you are logging in just for namesake means it's waste. You are now in hostel. All the students are in hostel for this hour.
Ma'am, in actually for boys in blocks there is no LAN connection, ma'am. Some of
Okay.
the blocks doesn't have any proper LAN connection. In my room
Okay.
also, I'm not getting LAN connection, so I just came to library.
Okay. 117 students I have seen where you are sitting. I should be knowing. Na? See, just giving a lecture is not a big deal for me. But if you are not listening that when I am teaching, it's of no use. No, I can just give a video lecture of the previous sessions and I can close the syllabus. No need to take extra pain, I am thinking, if you are not responding. Because physically you are not sitting and hearing, I can share my previous videos, no? That completes the syllabus. Goal of completing syllabus alone means I can share that. Goal of making you to learn means you people have to be attentive and you have to be giving me the answers for the questions whatever I'm asking. It's not happening. Say by this Friday, you give me what is the status, like how an offline class is held in the same format. We also will take.
Okay,
Varun,
okay, ma'am. Okay, ma'am. Will do.
Dheeraj is not there.
I think he's in blocks, ma'am. Like, blocks have power cut now, and there is also no LAN connection there.
But many have, I'm seeing here 107 students are there then logged in.
I don't know, ma'am. Like whether they might be joined with their mobile data or what.
That's the thing. Like logged in, okay, but not hearing the lecture is waste of my energy. What I'm thinking of. Okay, but by Friday you will let me know. Okay.
Okay, ma'am.
Yeah. Okay, I'll give the internal structure of this Bilbo, the built-in logic block observer. Say using 4 to 32 tabs, we have seen where you need to take the feedback. Okay, so we can have the same connectivity. The connectivities will be same, only the tapping points will be different. Okay, you can tap according to the points what are mentioned in the table. Previous classes I have given that table. Okay, Now see here, I would like to take the minimal one, 4-bit Bilbo, the structure, 4-bit Bilbo registry structure will take. So let us take that in a horizontal to vertical shift format so that connectivities will be a little bit easy to explain also. Now if I take this as D1, Q1, D2, Q2, D3, Q3, D4 and Q4. Okay. This is your earlier connectivity. These were the tap points, no? Q1 and Q4. This is your XOR. Okay. This is your feedback path. Now I'm taking that as a feedback path. I use a multiplexer to choose whether it is a feedback path or an external input. Okay. Because we said the modes as linear feedback shift register, multiple in signature register, or a what you say normal shift register format, or a normal operation we were saying. Okay. A shift registry means moving the data between these elements. Okay. A normal operation is something like external input getting dumped onto your registers. So this is something like I can say serial input sort of thing. And okay, I use the XORs for each flip-flop, one XOR for each flip-flop, and one AND gate to take the feedback. Okay. What you say, an AND gate here, one more AND gate here, 4 AND gates. Okay. This AND gate will be one of the input to the XOR. Okay. And these AND gates will have a common control. Let us have a common control for all AND gates, having a setup of, I'm taking this as an OR combination. This is OR gate. Okay. OR gate with an inverted and straight input. That means inverted means, say I name this as control 1 and this is control 2. Okay. And the mux, one of the AND gate will get the mux output as its input, and one more set of AND gates will use for defining the second inputs through a control signal which controls all the inputs of this D flip-flop. Now I take this C1 control, and independent circuit responses, after testing we get the circuit responses that will be fed through this AND gates. Okay. And now this AND gate output will be the input to the XOR element. Okay. Now this Q1, the previous output should be fed as the input to the next flip-flop. So that feedback will take that as the input to the D flip-flop. Like this I am connecting. This is the total setup of your Bilbo. Now this is the clock will be common. Comes clumsy, I am not drawing, but anyhow if you want I'll put this. The clock is common. This is system clock. Now the last one here, serial input, if you take this will be serial output. Normal operation. Now here the mux 2:1 mux. This is 2:1 means there should be one selection line. So C2 control. This is 0:1 will take, not 1:0. Okay, this is 0:1. This is 0:1 take. That means when C2 is 0, it will be serial input. C2 is 1, it will be the feedback part. Okay, if C1 is 1, then the response of the circuit under test will be taken to the XOR operators along with the feedback thing. That means these two inputs will be applied, means that that is your multiple in signature register. When there is a feedback path along with the system response taken onto your XOR, means that that is multiple in signature register. Without this, if you connect, it will be a normal feedback LFSR. Without Z connected to your D1 to D4, it becomes LFSR. Else it will be Z1. If these both are not connected, it becomes a normal operation. It becomes a normal operation. Maybe if you take the equations of this total circuit, this is 4-bit register Bilbo. Okay, 4-bit register Bilbo. Now we can write the equations. See, if you check the equations of D1, D2, D3, D4, D1 alone will be having the feedback parameter. D2, D3, D4 are similar. D1 will be different from D2, D3, D4 equation because only D1 has this feedback parameter. Okay, so if I take this as feedback, F is the output name I'm giving in. What is D1 is, check this D1, what is D1? This is, can anyone mention what is D1? No answer. Z1, C1, this one, Z1, C1, XOR with serial in. If you take, I take this as S5, maybe take this as S0. Now it is XOR one element we have defined, the other one is serial in C2 dash, because 0 selects C2, C2 dash selects SI. Okay, or the feedback, there is 1 will be coming with C2. If I'm correct. And not only that, you have one control here, that control is nothing but C1 dash or C2. C1 dash or C2. This is the equation for the first flip-flop. Then later of say D of I, if I take where I is 2 to N. 2 to N, anything you take. That means I is greater than 1, apart from 1, anything you can take. What is the equation we'll be getting? Corresponding Z of I, if it is D2, it will be Z2, D3 means Z3, D4 means for D4 equation, it will be Z4. Z of I, C1, XOR that, we are writing this equation, XOR that with the previous output fed back, see here, these are the previous outputs fed back. So Qi minus 1, what is that controlling? This is C1 dash or C2. Hope we have defined all the terms here now. See, here, this is the guiding equations what we are having. Now, if you can derive independent functionality of this bilbo, independently we need to derive the functionality of the bilbo, then we need to take the independent C1, C2 values and define what is the mode of operation. Okay, say if if you can take the combination of the control signals 0, 0, if I'm taking C1, C2 is both 0, 0. Now here see C1, C2 is both 0 means this will be 1. This will be 1, and C2 is 0 means this will be the serial input that is chosen as the input because C2 is 0. Okay, so these will be isolating the Z parameters onto your XOR. Only this SI fellow will be connected to your Ds. That means it is a simple shift register. If C1, C2 is 0, 0, C1 is 0, isolates Z to D. It will disconnect. And this will be connecting only this S of I to S of I will be connected through your what you say the feedback paths, because this C1 is 1. C1 dash will be 1. C1 is 0 means C1 dash will be 1. This feedback element will be there. So what happens is it is a normal serial in serial out format. So it's a shift register format. Okay. C1 is 0, C2 is 1. Control. C1 is 0, C2 is 1. See here. C1 is 0 means this one will be 1. C2 is 1. So this altogether is 1. That means it is choosing C. C1 is 0 means it is isolating Z1. It chooses only the path of your what you say the feedback element. The feedback element. C2 is 1 will be choosing the feedback path. So when the feedback element is there, which is with an isolated Z connection, means that it is a simple signature generator. So that is linear feedback shift register. Okay. If it is 1, 0, the control signals are 1, 0. C1 is 1. C1 is 1 means now these Z fellows will be getting connected to your XOR inputs. And C2 is 0. C2 is 0 means this one. The external data along with the system response, the external pattern along with the system response will be given to the XOR operator, means that it is testing the, or what is the, comparing the fault-free response with the system response. Fault-free response with the system response. Means that it is a normal iteration of, or what you say, the other way we can take is a normal operation of comparing the bits is performed. A normal registry operation. Registering the data, storing the data. Okay, next one is
Ma'am,
yeah,
ma'am, can you explain this one again? The normal one?
this one, normal operation. If C1 is 1,
Yes,
Z
ma'am.
is the response that is being analyzed. Z will be connected to your
Yes,
circuit.
ma'am.
Then C2 is 0. C2 is 0 means that is your serial data that you are, that means the pattern that will be given for analyzing, or what you say, normal shifting, normal value. Only this inputs along with your external input, if you are taking, what will be the iteration? Are you taking the feedback parameter? No, this is disconnected. No, Feedback path is disconnected.
Yes, ma'am.
Only the things that are connected will be your external inputs connected to normal shift register. Disconnectivities will be there. Disconnectivities are there. That means one flip-flop response will be fed to the next stage, next flip-flop. That means it's a normal storing of data.
But ma'am, I have one question.
Yeah.
In the OR gate at the bottom, if C1 is like if it's 1 0, then the OR output is 0, right?
This is it. This C1 is 1 0 means this is 0. This is 0. Means
So output
what
is
are
0
the things? No. Which output is 0?
of the OR gate.
This is 0. This is 0.
Yeah,
Okay.
so
So
if that's
this is
fed
0
into the
means
AND gate, then the input won't matter, right? Like the serial input isn't
you
considered because
won't
it's
get any of the feedback. That means this is disconnected, this is disconnected, this is disconnected, this is also disconnected. Only the thing what you get as the input is Z. Only these Z values will be updated to your D flip-flops.
okay, ma'am.
That means total this segment is disconnected. This feedback is disconnected. Okay, only Zs will be connected to your D flip-flops. That means a normal storage element.
Okay, ma'am.
Yeah, that's why we are
Thank
saying
you.
it's a normal memory storage buffer sort of thing. If this
Okay.
connectivity is there, then we said it is a serial operation. So it's a shift register. For 1 means this one. C1 will be 0, C2 will be 1. 1 means C1 dash. No, this is C1 dash, this is C2. This will be connected. Not only that, C1 makes this Z to be connected. Not only that, your C2 fellow here is 1, means that your feedback is there. So what are in total, what are the elements that are available for your D1, D2, D3 and D4? Is that system response, the feedback thing? That means this element is nothing but your linear feedback registry setup, and this setup is your response analyzer. Both the things you put together, it will be the generator response analyzer, means it is multiple in signature register.
Ma'am, it's just taking another previous output as an another input, na, ma'am. I mean, for example, here C1 becomes 1,
Which
C2
output?
becomes also 1, like previous one. After, for example, in D1 case, we only get Z1 XOR F.
No. Control of which combination you are telling? 1 0 or 1 1?
1 1, ma'am.
1 1. See 1 1. See here. For 1 1, obviously Z will be connected. Okay. Z will be connected. These are the system response. Okay. And C2 is 1, means that feedback is there. Until this is clear. Until this is clear. Now if here you take C1 is 0 or C2 is 1. That means any one of the thing is 1, your OR gate. It makes the feedback of the previous stage Q connected to D.
Yes, ma'am.
Doing so, you have an XOR operator here. Means that you are trying to analyze the system response. You are trying to analyze the system response with the LFSR. This setup is LFSR. This plus of the Z values, if you take, plus in the sense not OR operation, I'm saying these two responses, if you take onto XOR, what is that we are doing? It is MASR, multiple in signature registry. Your previous circuit you check. When we were converting LFSR to the multiple in register, what we have taken, each stage we have introduced an XOR operator, and each stage XOR operator will be provided with the system response. That means the circuit under test response, the circuit which is under test will be applied with one sequence. We give some sufficient time for it to generate its response. Then that we try to, what you say, response gathered will be applied to the LFSR. That means, what is the pattern that you are getting? Is it same as the fault-free response or different from that? It will be given by this XOR output. If it is 0, it says that they are same. If it is different, then we can say that there is an error happening at that particular bit. Am I clear?
Yes, ma'am.
Because the last combination, we are using the total circuit except the serial in serial out thing. That means extra we are not taking anything from outside. We are generating the test pattern within the circuit, because this setup lies on the circuit board itself, and this is the response what you take from the circuit what you are testing. That means the IC or the circuit setup what is on that IC, their outputs will be tapped and that will be analyzed with an XOR operation. That means you are doing a comparison. Okay, this is all about your, what you say, the testing of the sequential circuits, converted that into a combinational. Way back, if you can go to the beginning of the testing of combinational and sequential, what we said is combinational is a straightforward thing, but sequential needs an element of memory that takes much time and a complex pattern of analysis. So instead of taking that as a sequential, we convert that into a linear format, and that linear format makes the repetition of the combinational blocks in the circuit with every stage response taken to the next stages, every stage response taken to the next stages. So this is all about your testing of the combinational and sequential.
Ma'am, I have a question.
Yeah.
I have a question. So this one that you did was now for 4-bit, yes, ma'am?
Yes, yes.
So if we have to do the other ones, then how would the
Say,
design change?
you have 32-bit, or for that we have given a table. No?
Yes,
what are the
ma'am.
tapping points? Tapping points. The circuit setup will be same. Circuit setup will be same. Only the thing what we have to change is the taps. Where exactly the feedback should be given, the taps will be changed. Something like, say, if it is a 5-bit thing, what will be your feedback thing? Q2 XOR with Q5. I think this
Yes,
table
ma'am.
I have given you. No? That means
Yes,
instead
ma'am,
of
that's
taking this feedback here, we'll take from here. And this setup will be same. This setup won't be changing. Only your taps will be changing and number of inputs will be changing.
okay, ma'am.
Yeah. So that's what I was telling. You can refer to that table. Decide what are the feedback paths here. This total setup will be similar. You go on increasing the number of flip-flops, that's all. Okay. So further no questions in this regard. Maybe another topic will move on. Your adders portion will start now. Okay then. So different types of adders we have seen. That portion was there in DSD1. Now something like we need to go for what is called as fast adder concept, or block adders are there. Then multipliers we have. Multipliers is something like multiple shift and add format. normally when you take that into the physical representation or a circuit representation, we try to implement the multiplier using the adder alone. Okay, adder will be the basic building block, but repeatedly you do the addition, that becomes a multiplication. Okay, repeatedly you do the subtraction, that becomes a division. That is a theoretical way of explaining like how your adder or subtractor can be taken for implementing a multiplication or division process. But actually, when you take a concept of adder and subtractor, we never take this subtractor as a separate design, but we try to use something like a complement addition aspect to implement a subtraction. Okay, so any element of either you take adder, subtractor, multiplier, or division, everything will be implemented, including this adder, using the concept of adder alone. Only the adder is the basic block. If you can properly or thoroughly understand what is an adder, you can play with the circuit now. You can change that into any sort of adder, subtractor, multiplier, or division. Normally, division is something like repeated subtraction, we can say. That repeated subtraction is nothing but repeated addition of the complement. Subtraction is repeated addition, addition of the complement of the value. Multiplication, it is a repeated addition. That much is clear. Hope you know this logic of implementing a multiplier or a division using an adder. You know that. Normally, say if you are multiplying, say n bit and not n bit, let me take, say 3-bit multiplier. If you take 3-bit into 3-bit, if you are doing, what is the size or what is the result length? Will it be 3 or more? 3-bit multiplied with 3-bit value, something like 110 multiplied 1101. 3-bit multiplied with 3-bit. What will be your result you are expecting? That length of the thing. Will that result be enough having 3-bit, or will that result be in need of more than 3 bits for its result?
More than 3.
More.
So maybe you can expect that to be 6 bits, no? To the max. To the max.
Yes, ma'am.
Yeah, because something, if you take the multiplication operation, something what we do is the 3 bits will be taken as a shifted format, and you will be adding shift and add, shift and add. Okay, so you'll be getting the result something within that what you say 3 plus 3 n plus n. This is shift and add format. Anyhow, this multiplier will be having an operation of addition plus shifting. Okay, and how many number, or what you say, how many adders are needed? It depends on how many number of bits you are having in the multiplier and multiplication sort of thing. So a normal shift and add, if you take a normal block adder or fast adders you can use, but the complexity of the design or the number of bits or number of adders needed are more, and your cost of the design goes up. Okay, so we start with a simple logic of what is called as Booth's multiplication or Booth's multiplier, we call it. Or Booth's algorithm also. Few textbooks they give that as Booth's algorithm. Okay, here what is the concept is that you can multiply, you can add, you can subtract, or you can divide. Something like we have seen that in the sign, the magnitude, or 1's complement, 2's complement elements. Both numbers can be positive, one can be positive, one can be negative sort of thing, or both can be negative. That means multiple magnitudes, different magnitudes, positive, all positive numbers, mixed thing, that means one positive, one negative, or both being negative can be used. Only thing is, if positive value you are taking, you will be taking it as a direct value. A negative value you are taking means you will be taking a 2's complement of that value. Only blind way of remembering the procedure is that a negative number, if you want to handle, we don't take that as a negative number, rather we take the 2's complement of that value. Okay, that gives us again back any subtraction or division to be done means it is an adding process alone. You are adding the 2's complement. Okay, so this Booth's multiplier here is using a concept of either adding a true value if it is a positive number, or adding the complement value if it is a process of subtraction. Adding a complement value if it is a process complement if it is a subtraction that is needed to be done. Okay, so this Booth's proposal or Booth's algorithm says that if you are taking n bit multiplication, okay, so your multiplier defined by say q is multiplier, and accumulator something related to our microprocessor, and that element we are taking the same nomenclature. A indicates accumulator, wherein you are storing the data. That means here n bit means n plus n we are saying, no? So one portion of that n will be q, one portion of that n will be the accumulator. So these two are the registers we are using, some set of registry data. So q denoted by the multiplier parameter, a is the accumulator, which gives you the what do you say, the complete result when you take them together. Okay, so here one extra bit will be taken. I'll let you know the procedure now. If you are taking a I'll take an example of 4-bit Booth's multiplier I'm taking. Means that my q is having 4 bits and a should be naturally 4 bits. How many you are taking, that makes that same number of bits you are taking, and one extra padded bit will be taken just to have the analysis whether to perform an addition or subtraction or just a shift sort of thing. Okay, you know what is arithmetic shift? Arithmetic shift. No, arithmetic right shift or arithmetic left shift sort of thing. You must have read this in your microprocessors shifting operation. No, there won't be any answer. Huh? Arithmetic shift means from which bit you are, say right shift you are taking, what is the bit you are shifting, that value will be retained in that bit position. That is your arithmetic shift. That arithmetic shift will be done here. Okay, so thing is, if I'm having a 4-bit A and 4-bit Q, say if I take this as Q0, Q1, Q2, Q3, A0, A1, A2, A3, what we do is we pad that with 1 bit minus 1. Okay, and every time we try to see what is the bit value of Q0 and Q minus 1, these 2 bits will be found. Okay, if both these 2 bits are 0, 0 or 1, 1, if both these 2 bits, like we are adding 1 bit extra to the representation. So initially we try to take this as 0. Okay, then later we do the arithmetic right shift. When doing so, this value will be getting either 0 or 1 based on the Q0 value. Okay, so at a time we try to see what is the value of q minus 1 and q naught. If these two bits are 0, 0 or 0, 1, direct arithmetic right shift will be done. Means that, see here, this bit will come to A2, A2 comes to A1, A1 comes to A0, and A0 goes to Q3, Q3 goes to Q2, Q2 goes to Q1, Q1 goes to Q0, Q0 goes to Q minus 1, and A3 will be retained here. This A3 also will be. That is your arithmetic right shift. Arithmetic shift operation we are doing. Now, if this Q0, Q minus 1 is 1, 0, say, when you are testing or checking these two bits, it so happens these two values are 1, 0. Then what is the iteration that will be performed is, to the bits of A, that means A0, A1, A2, A3, we subtract the multiplicand. That means I am multiplying Q with M. That is the thing I am performing. So the Q bits are taken here on the Q register. Okay. And this multiplicand will be added to or subtracted to based on the value of Q0 and Q minus 1. So the multiplicand will be subtracted, means I will add the complement value, 2's complement of M to A. That is the iteration we will be doing. Then after that, we will be doing arithmetic right shift. These are the two iterations that will be performed if it is 1, 0. Okay. If it is 0, 1, Q0 is 0 and Q minus 1 is 1. Then and this will be stored into your A. Okay, you do this operation and store that into A. Now, when it is 0, 1, you do the iteration of adding A accumulator value with the multiplicand, store that in A, and do the arithmetic right shift. These are the operations you will be performing. And how many times you have to perform is how many number of bits you are having. That many number of times you will be performing. Say if you have 3 bit, 3 iterations, 4 bit, 4 iterations. So finally, after completing the n number of iterations, such iterations, these type of iterations, the final result will be the total A plus Q result what you get. What is the value you will be getting? Here is the result of the Q into M, the multiplier output. Understood? Verbal description is understood, or should I give some flow chart sort of thing? You need a flow chart, or you understood this? Yeah, any answer?
Yes.
Huh? You
Ma'am,
need
flow chart,
Can
please.
you give a flow chart? Can you
flow
give a flow
chart.
chart?
1 second, then I'll do one thing. Take this here. I'll draw here the flow chart. Okay. Something like at the beginning, you start the iteration I'm taking. What is that we need to do is just first take that size of A to be all equal to 0. Say 4 bit for 4 bit Android. Okay. And make all Q's to be there 0. Later we'll set it. Okay. Next, what you do? Dump the multiplier onto your Q. Then what you can say, M is your multiplicand. Just for understanding and all. Okay. Then say N is the number of bits. N is the number of bits. Here it will be 4, say. Okay. Now what we have to do is we need to introduce q minus 1, which is 0. These are the iterations at the beginning we do. Okay, then what you do? You take the q naught and q minus 1 bits. You check them. You check these two bits, q naught and q minus 1. Now we can have the branchings. Say if this is 1 0 0 1 0 0 1 1. This conditions I am taking. If this is 0 0 or 1 0, do the arithmetic right shift. Arithmetic right shift means a q q minus 1 altogether you need to shift. As I said here, a q q minus 1, all of it should be shifted. Okay. Then here what you need to perform is, if it is 1 0, this q naught q, a should be stored with a subtracted with its multiplicand. If it is 0 1, a should be stored with a added with the multiplicand. Then do the arithmetic right shift. That means whatever may be the value of q naught q minus 1, your arithmetic right shift is happening. Okay, this is for every step, but with an padded operation of either adding or subtracting the multiplicand to the accumulator. Okay, then how many times we need to repeat this? We use a decrement counter sort of thing. You decrease the value of n. N is 4 if you take here. Every time we try to decrease this. Okay, and if n is, after decreasing, check whether if n is 0. Okay, if n is 0 is true means stop. If it is false, then what to do? You have to again go back to this step. This step has to be done. That means again you take the q naught minus 1, q naught and q naught minus 1 value and do the operation. Okay, this is the flowchart. Now maybe we'll take one example then. Maybe you can understand this little bit more clear. Say we'll take a 4-bit itself. Say multiply 3 with 7. Say what should be your answer? Positive number I am taking. It should be 21. Okay. So say I'm taking m as 7. If I represent this, this should be 0 1 1 1, 4-bit. And q is 3. That means this is q into m I'm taking. Q is 3. That means this should be 0 0 1. Okay. Okay. Now what is that we need to do is a q, that means 4-bit, and q minus 1 will take. A is initially 0 0 0. First step I am taking in. And q is 0 0 1 1. And this q minus 1 is 0. Now check this. This bit and this bit you check. Because this is q naught and this is q minus 1. This is 1 0. 1 0 means what is that to be performed? Here 1 0. It a minus m, that means it should be subtracted with the multiplicand. Either you can add that with the complement. So if I take the complement of this, what is that? 2's complement we need to take. This is 2's complement. Okay. Whenever there is minus of m parameter, we try to take m complement and we add it. If it is direct plus of m means direct this value will take in that. Okay. So this is for plus m, this is for minus m, this value. Now what we have to do? We need to add the complement to this one. That means adding the complement means this one will be adding. If you add, what is the result you'll be getting is 1 0 0 1 0 0 1 1 on Q's, and this is 0. Then after this, what we have to do, this is A minus M performed. Then arithmetic right shift has to be performed. Arithmetic right shift means this one comes here, this one comes here, 0 here, 0 here, this 0. And this one comes here, 0, and this one comes here, this one is arithmetic shift. Okay, now this is first step completed. Now again check this values here. This Q0 and Q minus 1 are both 1. The second step now. What is that to be done? If both are 1, it is a simple arithmetic right shift. So do the simple arithmetic right shift. This 1 comes here. Okay, this is 0. This is 0. This 1 comes here. This 0, 0. And this is 1. This is 0, 0, 1, 1. And we are doing arithmetic right. So now here one iteration is over. N is 3 here, N is 2 here. Next, this completes the second step. Third step, again you check for the Q0 and Q minus 1. What is to be done now? This is 0, 1 it is saying. 0, 1 means directly you add this to A. That means A plus M has to be done. A plus M means 1, 1, 1, 0 will be added with 0, 1, 1, 1. And this is 0, 1, 0, 0, 1. Now what is the result you get? 1, 1, 0, 1, 0, 1. Maybe that you can discard it. Okay, this is discarded. Now only this is left. Let's see here. 0, 1, 0, 0, 1. Now the next step is arithmetic right shift. Arithmetic right shift. So we're doing so, this will be 0, this will be 0, this is 1, this is 0, this is 1, this is 0, 1, 0. What next? This is 1, this is 1. Am I correct?
Ma'am, you told to discard now, ma'am.
Yeah. This is 0. Sorry, this to be discarded. 0. Next. So one more step is left for us now. After doing this, both are 0, 0. Both are 0, 0 means what is that? Just shifting the total arithmetic right shift. So arithmetic right shift means this is 0, this is 1, this is 0, 1, 0, 1, 0, 0, 0. Now, how many 4 iterations are complete? See here, this is first iteration, second iteration, 1, 2, 3, and this is 4. 4 bit, now that becomes 0. Every time we have to decrement this by 1. Now, total complete if you take, this should be 21. If you check that, you'll be getting the answer. A, Q combined, you will be getting that as 21. AQ, I'm saying AQ, not Q minus 1. You shouldn't take Q minus 1. That becomes different. This is 1, 2, 4, 8, 16. So 16 plus 4 plus 1, 21. Complete. You try to do for any other value. Hope everyone understood what is Booth's algorithm, Booth's format of multiplication.
Yes, ma'am.
Yes. Yes, ma'am.
Do one thing. I'll give you one minus 4 multiplied with minus 4 multiplied with minus 5 multiplied with 4. Answer should be minus 20. Means that your answer will be in 2's complement. When you take AQ, this one, your answer will be in 2's complement. Okay. And how do you take a minus value is take this representation as the 2's complement of that. That means plus 5 will be 0, 1, 0, 1. Minus 5, you need to take this as 1, 1, 0. Okay. This will be now your Q. You store that in Q. Or you can take this as Q. Anything, this or this, anything means the same for us. 0, 1, 0, 0. Either you take this as Q or you take this as Q. QM or MQ means the same for us now. Result is same. You do this. I'm giving you this as assignment. See, using Booth's algorithm, do the multiplication of minus 5 with 4, minus 3 with minus 7. Oh, not 7. I'll give another. Minus 3 with minus 6. Both negative. Both positive we have done here. You try to do this too and put it in assignment. This is one question. Okay. The other.
Ma'am?
Yeah.
For this Q minus 1, we should take as minus 1 or, I mean, 1 or 0?
0. Minus 1 bit at the initial stage, it will be 0 only. First, we initialize that with 0. This point you are asking, na?
Yes, ma'am.
This will be 0 only. Only this values depends on what is the magnitude you are taking here, whether it is positive or negative. Okay? Because ultimately, when you are finally getting the answer, that will be the answer of AQ only. This is only for testing the operation that has to be performed. Testing the bits for what operation to be performed. And see here we are taking 2 bits alone, and we were getting the output based on how many number of bits we have, that many number of steps we are performing. Here there is some modification that is done for the Booth's algorithm, and that is called as a modified Booth's or modified Booth's algorithm or a recoded multiplier, it is called. A recoded multiplier. This I'll take tomorrow. Or what you say, bit pair multiplier. Many names are there based on the author or textbook you are following. They give this as with different titles, but the procedure is same. Bit pair multiplier, recorded multiplier, or modified Booth's algorithm means the same. Here, what is the difference is, for the previous one, we have taken only Q0 with Q minus 1 we have taken. That means 2. But here we try to take 3 bits together. It's not only Q0, we try to take Q1 also. Q1, Q0, Q minus 1. Okay. And we try to see that it is bit pair we are saying. This is one pair, this is one. This is another pair. This is one pair, this is another. One and second. Bit pair will take. And we try to use the logic of whether adding or subtracting or multiplying sort of thing based on the value of the bit pairs we are getting in. This I'll take tomorrow, not today. It takes time for explaining. If any doubts are there, you can get them clarified here, or else we'll stop the class now.
Ma'am, I had a question.
Yeah.
I'm pretty sure you'd have said it though. In the example, why did we take 4 bits for M and Q when they can be represented in 3 each?
Yeah, you can take just for explanation. I took 4-bit.
So even 3 would be fine.
Even 3 also, you'll be getting the same answer.
Then the number of iterations would come down to 3.
3. Just for explanation, I took that as 4-bit so that we get the clarity of the procedure. That's all. Because the more the number of bits I took, here you were getting more steps. No, here that shift operations and all. Direct 3-bit you can take.
Okay, ma'am.
Actually, then a count or the steps needed is depending upon the magnitudes of your multiplier and multiplicand. Okay.
Can
The
you
previous
explain
example.
that?
3-bit is enough. Actually, 3-bit is enough because it is only this thing, 0, 1, 1 and 1, 1, 1. That is enough.
Okay, ma'am.
Explanation, I took 1 extra bit. That's all.
Okay, ma'am. Thank you.
Yeah. This procedure, if you take the same answer, you have to get. You check it out. Check it out with 3-bit also. Do this with 3-bit. Only take this and find out whether you are getting the same answer or not. What is that you will be doing is the arithmetic right shift. That takes care of your result. Okay, take this one also. This one also you try to implement using 3-bit. Using 3-bit, check result of 3 into 7. Okay. No further questions. I'll stop this session. Okay, we'll close.